Okay, any questions before we get started today? So we're going to do the opposite of reduction, so oxidation conditions today. So the oxidation state is increasing, and as we'll see, that can happen in one stage or two stage. We'll look at the alcohols we're starting with, and then using some logic predict what carbonyl groups they can become, and then really differentiate between one and two stage. So two stage means it's going up two oxidation states. The general mechanism for an alcohol oxidation is shown here, sort of independent of what reagent we're using. So you have to start with a primary or a secondary alcohol. This do not work with tertiary alcohols. So the constraint is that you must have a hydrogen atom on the carbon bearing the OH group. And so alcohols by their nature are OH, so you have a second hydrogen. So what is happening overall is you're losing a molecule of H2. It doesn't necessarily happen as like H2 itself, but equivalent of that. So the first step is usually activation of the oxygen atom. So we know that, I'm going to just call this that carbon alpha. So we're going to do an elimination. That means forming a pi bond. H is a bad leaving group. So as a leaving group, it would be H minus, and that's hydride, and that's bad. So really, we got to activate the oxygen by getting rid of that hydrogen. And so when we do that, we're essentially substituting the H for a leaving group. And once we do that, the mechanism that follows is what we learned from Organic 1. It's an E2 reaction, so a bimolecular elimination. So that hydrogen on the alpha carbon gets abstracted. So that's this arrow here. The electrons then form the pi bond, and then the leaving group will leave. So overall, it's a formally an equivalent of losing H2 across that CO bond. And then you end up with your carbonyl. And then you have the conjugate acid of the base that you started with, B, and then your leaving group. And so those charges balance. So for the individual reaction conditions, I'm not going to show you the mechanisms for each, because they're basically following this general protocol. We'll see some mechanisms for some other things, but the main thing is, based on the reagent, that really the way they differ is how this H gets substituted for a leaving group. So to review what's possible and what the strategy is, this is the oxidation state ladder. So oxidation state is OS. And we have a couple situations here. We'll call this case 1, case 2, case 3. So we know that if there's no heteroatom, it's oxidation state 0, and that would be an alkane. If we go up to OS1, as we see in this first case, that would be ethanol. That's a primary alcohol. That alcohol can be oxidized to an aldehyde. So if the key here, or the clue, is if the alcohol is at the terminal position, it's going to form an aldehyde. And it can go up one more oxidation state to the acid. So essentially, you have to have a primary alcohol to go to an acid. In the second scenario, you'll see that a secondary alcohol can only go to a ketone. And again, the reason for that is this H right here. You only have one of them. So once it gets eliminated, there's no more H's on that carbon. So secondary alcohol can only go to a ketone. In the third case, notice the tertiary alcohol, it cannot go up in oxidation state. So we have OH and then a carbon with 3 other carbon substituents. So a tertiary alcohol has no hydrogens to eliminate. So that's summarized. Primary can go to aldehyde. So the difference between that is 1. So 2 minus 1, that's a 1-stage oxidation. Or then depending upon the reagent you use to the acid, so 3 minus 1, that's a 2-stage oxidation. Secondary alcohol can only go to the ketone, and tertiary you can't do anything with. So in a sense, you can sort of get some chemoselectivity with differentiating things, but as we'll see, if we have multiple alcohols in a molecule and we only want to act on one, then we're going to learn some reactions to protect those alcohols. And I guess in Module 5, we'll sort of revisit some of this chemistry when we talk about carbohydrates. Carbohydrate is just a carbon chain with a lot of different OH groups on it. Yep.
Can a primary alcohol go straight to carboxylic acid, or would it have to become an aldehyde first?
So the way that mechanism will work is that it does proceed through an aldehyde. And then the issue there, as we'll see, an aldehyde has no OH group, right? So an aldehyde has to get transformed into something else, and then that gets oxidized. So we'll talk a little bit mechanistically about that. So here's a question about classification based on the nomenclature. And the key word here is can't. So regardless of whatever reagents we're using, one of these cannot be oxidized. So A. So let's draw that out. So we see the parent is 4 carbons. The alcohol is at the 2 position. And then at the 2 position as well, we have a methyl group. So that means it's a tertiary alcohol. So to practice the other logic, if you oxidized 2-butanol, what functional group would it become? A ketone. So secondary alcohol has to go to a ketone. And then 1-butanol would become an aldehyde. So on these, we can see the difference. So the ketone has no hydrogens remaining. This has one H remaining. But then the oxygen doesn't have an H. So you can form that aldehyde and further oxidize it under a certain set of conditions, but it has to form something else first so that you do get an OH group. So the conditions for one stage, so you're just going up one number. A primary alcohol becomes the aldehyde, secondary alcohol becomes the ketone. So there's three conditions. Let me scribble this out so that the statement is true. So as I said, a lot of these just have a name of the reagent or a name of the person or people that have discovered the reaction. So the first set of conditions is called PCC. That's not PCP. It's PCC, so pyridinium chlorochromate. You'll see the structure on a slide coming up. So again, the main thing about this is when you see the reagent name, you make the association with it's an oxidant in its one stage. And then from there, you're just classifying, is it a primary or secondary alcohol? The Swern oxidation. So this is an actual person. So Swern was a professor at Temple University. And then the last conditions are Des-Martin pyridinane. I'm from Wisconsin, so we call it Illinois. So they were at the University of Illinois, Urbana-Champaign. So all of these conditions use very different means to do the oxidation. The PCC is probably the most classic. One of the first ones discovered probably over 125 years ago. It uses chromium, and we all should know that chromium is bad for the environment. So it's a heavy metal. It gets like into the soil, into the water table. It's hard to purge. And it has some other sort of issues with functional group compatibility. And those reasons are why these other people investigate different methods for doing oxidation. So I'll show you the structures of the reagents, but again, the important sort of learning thing is knowing what the name of those reagents does in terms of the functional groups. So PCC is pyridinium chlorochromate. And so it's an orange solid. The solvent that you run it in is dichloromethane, and then just 0 to ambient temperature. So pyridinium is the protonated pyridine. So pyridine is this aromatic heterocycle. And when it's protonated, it's called pyridinium. And then the counter ion is the chlorochromate. So this is the thing right there that will activate that H to make it a leaving group. So since we're starting with a primary alcohol, we end up with the aldehyde called benzaldehyde. Has anyone ever smelled benzaldehyde? So it smells like almondy, really intense almonds. So say, for example, just to show, say you had that, phenethanol. So that's a secondary alcohol. PCC would then make that into the ketone. I guess one nice thing about these chromium reagents, when you stick them in, they're orange, and then as the reaction proceeds, they usually change color because the oxidation state of the chromium changes. So it'll turn like a boogery snot green, and then you kind of know it's done. And then you just filter off the gunk, hide it in a cabinet, and let the person next 15 years deal with it. So that's one of the issues is chromium. It's just a pain in the butt for waste disposal. And so that's why these other conditions exist. So the Swern oxidation is, for lack of a better way of saying this, it's a brew of a lot of things. And the oxidizing agent is this sulfonium chloride. So the alcohol attacks that and makes it a good leaving group. And as we've seen, we're starting from a secondary alcohol, so that makes a ketone. So maybe I have a little time I can show you what is happening here. So you start with this reagent. That's called oxalochloride. And then you use DMSO, so dimethyl sulfoxide. And that step has to be done at -78. So that's a cryogenic temperature. Those two things will react to form that sulfonium chloride. So what will happen? We get an oxygen addition to the carbonyl. So kind of like we've seen before, a nucleophilic attack. And this is kind of a preview to the next module as well in terms of arrow pushing. So that thing's not happy. The negative charge will collapse back down. And now it's going to eject Cl minus. So that chlorine will leave. So now we've balanced the charges. The sulfur is still plus, the chloride is minus. So negative is attracted to positive. So chloride attacks sulfur. And now this is where something kind of weird happens. We're going to break that sulfur-oxygen bond. That's going to form CO2. And then when this bond breaks, the electrons go on the carbon. That forms carbon monoxide. And then we get the charge balance Cl minus back. So depending on, sort of the dilution with the dichloromethane solvent, you might see this bubbling as that gas has evolved. And so that sulfonium chloride is the active thing that removes the H from that oxygen. So what you'll notice in here is there's no heavy metals. There's no chromium, there's nothing like that. So it's a fairly straightforward reaction to run. If you had a primary alcohol and you did this, you'd end up with the aldehyde. So Swern's okay. It takes a couple hours to run, just based on the order of how you have to add things. Probably the easiest one to run is the Des-Martin periodinane. So it's abbreviated DMP. And what's special about this is halogens typically form how many bonds from your Lewis dot? Just one. So how many does this have? 5. So iodine is what's known as a hypervalent reagent. So it can go past its sort of normal bonding pattern. And here's a Gen Chem question for you. An atom with 5 bonds is what geometry? Anybody? So it's trigonal bipyramidal. So you have basically a triangle. Oop. Then you have these other 2 ligands. So the iodine sort of sits in the middle. So iodine's really nice like that because you can form, there's a lot of these type of reagents, these Des-Martin periodinanes. So how does this thing work? It has these 3 OAC groups. AC is just, it means acetate, it's an ester. So it's a good leaving group. So oxygen has 2 lone pairs. We can see that the iodine itself is in a pretty high oxidation state, and it wants to get rid of one of those acetates, so that's like an SN2 reaction. and that's what will activate the OH group. So the AC, so that's what that means, acetate. So that's a base. We have this acidic hydrogen. So it can pluck that off. And then you end up with the sort of neutral species. And then in general, I haven't shown it here, but these, you can buffer these with an external base, sodium bicarbonate, or if there's just extra acetate floating around, that can do the elimination. So I'm running out of room here, so I'm going to abbreviate some stuff. So we're at this point. So that's how the H gets substituted. Then you have your acidic hydrogen here. And that does the E2 reaction. So again, these are nice because that DMP reagent is just a white solid. You chuck it in there with your alcohol. You do thin layer chromatography. And then the byproduct, this whole iodide thing, crashes out of solution and you just filter it off. So as I stated before, a secondary alcohol, you do the same thing and give you a ketone. Any questions? Yep.
I didn't quite understand the last diagram you structured.
So the ball is just the rest of the molecule. This is the carbon bearing the oxygen, and now this whole thing is a leaving group. So this hydrogen is acidic so that acetate can abstract it. Then these electrons, I guess I drew that kind of bad. The electrons from this bond flow in to form the pi bond. And then this bond breaks, so iodine will end up with a lone pair. So PCC, Swern, and Desmartin conceptually all do the same thing depending on what class of alcohol you start with. So those were all one-stage oxidations. A two-stage oxidation can only occur with a primary alcohol. So these conditions, as we'll see, so we're at oxidation state 1, then we went to 2. Notice in the aldehyde, there's no H on the oxygen. So the question is, how can that go up an oxidation state if it has to do an elimination? Well, it turns out the aldehyde functional group under acidic conditions, so aqueous acidic conditions, forms a functional group called a hydrate. The key thing to remember about this is it's still at oxidation state 2. So there's been no change in that. However, the main difference is this is sp2 hybridized, and now this is sp3 hybridized. And this has the H that we need. So you can sort of see from the hydrate structure, if you eliminate the two H's that are circled in blue to form a pi bond, that's going to get you to a carboxylic acid. So on the next slide, I'll just show you the mechanism of how the aldehyde becomes the hydrate. So again, it's important to remember the conservation of that oxidation state. As we saw a couple lectures ago, since we're under acidic medium, oxygen must be neutral or positive. So the first thing we have to do is protonate the carbonyl. So we do an acid-base reaction. And then if we see, by looking at resonance, the resonance will help guide us where the nucleophile will attack this thing. So in that form, the carbon bears the plus charge. And so after we used hydronium as the acid, we generated water. And now water is the nucleophile that can attack that. And then to get to the hydrate, we just do a proton transfer. And again, the key thing is for the two-stage oxidation, it has to proceed through this so that both the carbon and the oxygen have their hydrogens to eliminate.
So the hydrogen from the top one goes to the water. That's what happens.
Well, once we form the hydrate, then a different base will be used to deprotonate this. So
What about the hydrogen in the OH in the bottom one?
this,
Yeah, that hydrogen, where did it go?
so it's just going to reform hydronium. So the reagent that does this the most effectively is called the Jones oxidation. You may have heard of him, Indiana Jones. Kidding, it wasn't really Indiana Jones. So some dude named Jones in Great Britain, like seriously 125 years ago, discovered this. So it's an easy reaction to run, but again, it's kind of nasty because you take chromium trioxide, which it almost looks like coal. It's like black and powdery. It almost conglomerates into a goo almost. And then you dissolve that in sulfuric acid and acetone as your organic solvent. And that forms this, which is chromic acid. So it's a strong acid, plus it's got chromium, so there's all sorts of fun stuff going on here. Operationally, again, it's pretty easy to run. You just form a certain molarity of the chromic acid, you dribble in your alcohol, you'll see a color change, and then you sort of know it's done. So at that point, this primary alcohol, benzyl alcohol, would become benzoic acid. So under these conditions, because sulfuric acid, concentrated sulfuric acid is 2% water. If you start with a primary alcohol, you're always going to get the acid. It will not stop at the aldehyde. So again, we've gone from oxidation state 1 in blue there to 3. So after we learn like the stuff in module 3, you'll know like most of the reactions we need to know. And the strategy there is you're really looking at oxidation states and how to access functional groups. Any questions? Another way of doing it uses potassium permanganate. Potassium permanganate and water will do this. This forms like a purple liquid. Students do this, they tend to stain their fingers and their clothes, so you kind of know that they've been working with it. I would say it's probably lesser used, but KMNO4 is pretty cheap, so it's still a valid transformation. So again, oxidation state 1 to 3. So there's 2 ways that we can do that. I think some questions are coming up. Yes. So which of the following alcohols can be oxidized to the carboxylic acid with chromic acid? So this, the clue here is the alcohol must be primary. What'd you say? So C. So we have a 4-carbon chain, alcohol at the 1 position, and a methyl group at the 2 position. So that's a primary alcohol. So I would say don't get fooled by B. Even though it says 1, there's also a substituent at the 1 position. So that's a tertiary alcohol. I guess the same thing holds true for D. That would also be tertiary. Questions? Yep.
So we are forming carboxylic acid from primary alcohol, we are not forming aldehyde in between, right?
It goes through the aldehyde, and then the aldehyde becomes the hydrate, and then the hydrate is what gets oxidized to the acid.
So everything is like happening together, whatever we learn.
Yeah, I mean, so time-wise, it has to happen sequentially. So the primary alcohol doesn't just hop over to the acid. It has to form the aldehyde first. That aldehyde has to form the hydrate, and then that hydrate is what gets oxidized.
So if you want to stop at the aldehyde, we don't add some specific reagents to form that acid, that's what we do? If we
If-
just want the aldehyde?
Then you would have to use PCC, Swern, or Desmartin.
Okay.
You couldn't use the chromic acid.
Yeah, makes sense. Thank you.
So for the next run of slides here, so those are the oxidation conditions. Again, there's sort of two main sets, the one stage versus the two stage. And so we learned how to make alcohols using reductions of carbonyls. And so now what are some reactions of the alcohols? So as I mentioned before, sometimes you want to protect the acidic H group of an alcohol. So you don't want it to form the negatively charged species, the alkoxide, and you don't want it to form the positively charged species, the oxonium. So you have to substitute that H for something else. And so this is called a protection. And the reagent that's used is shown here. So tert-butyl, that's this part. Dimethyl, that's these two methyl groups. Silyl, Silyl is the silicon, and then the chlorine is the chloride there. In the periodic table, we have CNOF. Below carbon is silicon. So things that are in the same group have like the same type of chemistry. So silicon bearing a chlorine, that's a good leaving group. And what happens is just an SN2 reaction. So that oxygen will attack that silicon and displace the chlorine. And then we have a base in there. That soaks up the HCl that's generated. So if we look, I'll highlight it in blue here. This H has now been substituted for that whole group. And now the oxygen's kind of neutered in a sense. It won't do acidic or basic chemistry. So once we have it on there, how do we get it off? We get it off using an SN2 mechanism. With this reagent, tetra means 4. Tetra N-butyl, so there's 4 butyl groups. Ammonium is the plus, nitrogen, and then fluoride. So you have this fluoride anion. And so that's hot to trot for the silicon, so it'll attack it. And then it'll cleave that bond, revealing the alcohol. So that's a protection and then a deprotection. And so now we have our H back. So this thing's abbreviated TBAF. So again, mechanistically, it's just an SN2 reaction. Questions?
Nitrogen connected to really has no effect on the style either.
Correct. So it's there just as the cation for the F minus. So that tetrabutyl ammonium thing, there's a lot of reagents where those chains are different. So the reason they're so long, it helps make, because you have N plus F minus, that's a salt. So the longer those chains are, the more organic it is. And so then it's soluble in the solvent, THF. So like Na plus F minus, in theory would do the same thing, but sodium fluoride is not going to be soluble in organic solvents.
That's the whole structure.
So that's protection, deprotection. What if we want to transform it into something else completely? So functional group transformation. So we can take an alcohol, treat it with thionyl chloride. So it's that structure there, SOCl2. And then it basically, it's substituting the OH for chlorine. So I figure I'd show you the mechanism of this. It involves some interesting arrow pushing. So by looking at it, we can like recognize a couple things. We have to get rid of that oxygen, and we have to substitute it with a chlorine. So what happens to the other stuff? Like the other chlorine, why is there this pyridine in there? What purpose does that serve? If this sulfur was a carbon atom, do you know what that molecule is called? Any history buffs in the room? World War I. That's called phosgene. You ever heard of phosgene? So it's a chemical weapon. It's basically, you get a tank, you open it, and hope the wind's blowing in the right direction towards the enemy soldiers. That chlorine is at, or the carbon here is at oxidation state 4, right? So it wants to react. Sulfur is kind of the same way. Thionyl chloride, they have two very distinct smells. Phosgene Smells like cut grass, fresh hay. Like it's really astringent smelling. Thionyl chloride to me smells like vaporized rust. I don't know. I can't think of any other way. It smells sort of metallic-like, and you know it's not good for you. So because they're at such a high oxidation state, the oxygen is going to attack it. And then the first thing we'll do is break the pi bond. Sulfur has a lot of heteroatoms bonded to it. It wants to start shedding them. So that's an addition, and then it will do an elimination. And so a chloride Cl minus comes off. And so we've now balanced the charge, and really what we've done is we're transforming that oxygen into a good leaving group. So that's like an SN2 reaction. I can just draw it over here. But then we have this other thing that's formed. And so that's where the pyridine comes in. So that will act as a base to abstract the hydrogen. We form a second oxygen-sulfur pi bond and then eliminate chlorine. So we get this pyridinium chloride. And then SO2 gas, which bubbles out and attacks anything metal that's in the lab, turns it green eventually. So they're easy reactions to run, but they have some negative aspects to them. So the purpose of doing this, OH is a bad leaving group, but chlorine is a good leaving group. So once you have that halogen in there, you can do any sort of other SN2 reaction you want to do. Any questions? Yep.
Sorry, for the so the pyridine is attacking the hydrogen, which is causing the hydrogen-oxygen bond to. I'm confused on that one right there.
So I could draw it maybe with one more step in between. So this is a base. And that's an acid. This thing's going to self-eliminate. Yeah.
Sulfur had a larger octet, more than 4 bonds going into it. It's capable of having a larger octet.
Yeah, it can.
So it doesn't
So that's how you make chlorides. You can make bromides using this reagent, PBr3, and that stands for phosphorus tribromide. So phosphorus is below nitrogen, so it's trivalent. It does have a lone pair, which isn't shown. But if you look at it, it has these 3 bromines bonded to it. So again, it's not happy. Those are good leaving groups. And phosphorus oxygen bonds are really strong. So when in module 5, when we start talking about DNA and the phosphate groups, we'll talk about why did nature choose phosphorus as that atom to link the sugars in DNA. So the oxygen of the alcohol is going to attack that phosphorus. And then we sort of do the same thing where the bromide anion comes back around because now you have a good leaving group. The take-home message here is, again, you're substituting OH for Br, so a functional group transformation. And what do we got? Our mechanism. So really for this, since that phosphorus has 3 bromines, in terms of a stoichiometric ratio, you just need 1/3 of a mole for every mole of alcohol. So oxygen attacks phosphorus. We only have one type of bond to break. So a PBr bond. And now we've transformed the oxygen into a good leaving group. So bromine attacks that carbon. We cleave the CO bond. And that species can react 2 more times. So again, pretty straightforward. Operationally, handling PBr3 is, you need to take some precautions. It's kind of nasty stuff. You know something's bad when you open the bottle and the moisture in the atmosphere causes it to fume. You take a little sniff and then your nose starts burning a little bit. Then you want to hold it that far away. Or let an undergrad do it. So that's how you make bromides. One last reaction here in terms of activating the OH group into making it something that's a better leaving group. These are called sulfonate esters. So the problem, again, OH is a bad leaving group. So if we want to substitute it, we have to get rid of that H. And so in this reaction, we're taking that H and then transforming it into that. The whole thing with the oxygen, that's called the sulfonate. And so now that's a better leaving group. To make those, we use sulfonyl chlorides. So the sulfonyl group is SO2, and then there's the chlorine. The chlorine's the leaving group of that. So the mechanism, got to take a snapshot of what that is in my mind here. So that's a sulfonyl group. So methyl sulfonyl, and then there's the chlorine. I'm just going to say R3N for the amine base. So I'll show you the mechanism, but what's happening is see the H and the Cl. Some books will just call this lasso chemistry, like you're lassoing those out, and then you're forming an OS bond. So same deal, oxygen attacks sulfur. We break a pi bond first. And so now we have that really funky looking intermediate there. So that then collapses. That's not right. I guess what's different about this is that chlorine under these conditions is not nucleophilic because the presence of this base it's going to form that ammonium, so N plus, that's attracted to that Cl minus. So that attenuates the nucleophilicity of the chlorine. And now you end up with this sulfonate, which is a good leaving group. Questions? Ten more minutes. I'm almost out of Coke. I'm almost out of caffeine. I'll make it though. Don't worry about me. So again, why are we using this? We want to make that hydroxyl group into a good leaving group. The two most common sulfonyl chlorides, other than that methyl one, the trifluoromethyl is the best leaving group you can get. And then we have this aromatic ring. So that's a methylbenzene. The reason that would be used is because, as we learned in the beginning of this semester here, the benzene ring is a chromophore, so it's UV active. You can track the reaction progress by TLC. The CF3 group or the CH3 group, you can't really see it by TLC, so then you're like, how do I know when the reaction's done? So here's an example where we're now sequencing all of this stuff together. We want to take 2-butanol, treat it first with PBr3, then magnesium metal and ether, and then ethylene oxide, and then finally acidic workup. And so the question is, what is the name of the product? Any guesses? So let's draw the product of each step, and we'll see how it evolves. So step 1, we'll recognize that that reagent is going to substitute OH for bromine. So we get a secondary bromide. So I'm showing you the polarity in there just based on the difference in electronegativity. You remember what magnesium will do to an alkyl bromide? So it's going to invert the polarity to form a carbon anion. So now essentially that carbon is negatively charged, so it's a nucleophile. And we're reacting it with a 2-carbon electrophile. And in the last step, we're protonating. So if we number the alcohol with the lowest number it can get, that's carbon 1, 2, 3, 4, 5. So we should have a 1-pentanol. And then we see at the 3 position there's a methyl group, so that's going to get us D. So if you see these on the next exam, the best strategy is just to draw the product for each individual step to see how it's evolving. Any questions? So this is the sum total of your organic 1 and 2 knowledge right here. So you know now how to make alcohols. We can transform the OH into a good leaving group. And then this is just the summary of all the SN2 stuff that we learned from organic 1. So there's the FGT, functional group transformations. So if I highlight here, that stuff in blue, you're substituting that for any of those nucleophiles. And then it tells you what the name of it is, where you would see something in IR, mass spec, or carbon NMR. So really that's a lot of the tools. And now what the game is strategizing how you're going to sequence reactions to get to a desired product. Questions? I hate to rip you off of 3.5 minutes, but I'm getting a little hot and the caffeine's wearing off. So we'll start on Wednesday with ethers. So we'll talk about ethers and then see how far we get. The last part of this module is amines.